Have you ever wondered how your phone just instantly recognizes your face? Or how a self-driving car can spot a pedestrian on a busy street? Well, it's not magic. It's an incredible technology called Convolutional Neural Networks, or CNNs for short. So let's dive in and unpack exactly how we taught computers the art of seeing.
Really, it all boils down to this one simple question. See, to a computer, a picture isn't a picture. It's just a giant grid of numbers, pixels. So how in the world does it get from that massive spreadsheet of numbers to recognizing something as complex as a cat, with its whiskers and its pointy ears and its tail, without a human programming a rule for every single one of those features? Well, that is the exact puzzle that CNNs were designed to solve. So in this explainer, we're going to break it all down. First, we'll look at why this was such a hard problem to begin with. Then, we'll explore the brilliant inspiration we took from biology. We'll open up the CNN toolkit, see how we train them to get so smart, explore where they're showing up in our world, and then we'll wrap it all up with a really simple analogy to make it all click. All right, let's start with section 1, the seeing problem. Because before CNNs burst onto the scene, trying to get a computer to reliably see and recognize objects, well, it was a massive, and honestly, a pretty frustrating challenge.
The old way of doing things was called manual feature engineering. Just imagine trying to sit down and write code for every single thing that makes a cat a cat. You'd have to define the exact curve of an ear, the texture of fur, the angle of a whisker, for every possible cat in every possible lighting. It was slow, incredibly brittle, and frankly, the performance was just not very good. The massive leap forward with CNNs was this shift to automatic feature learning. Instead of us telling the computer what to look for, we just show it thousands upon thousands of cat pictures and it figures out the important patterns all by itself. That one shift is what unlocked the revolution in machine vision.
So where did this amazing idea for automatic learning even come from? Well, that brings us to section 2, a biological blueprint. And it turns out the answer was inspired by the best vision system on the planet, our own brains. Way back in the 1960s, two researchers, Hubel and Wiesel, conducted these groundbreaking experiments that revealed something incredible about how we see. They found that individual neurons in our visual cortex don't see the whole picture at once. Instead, each neuron has a local receptive field, which means it's only responsible for a tiny patch of our vision, and it only fires when it sees a very simple pattern, like a horizontal edge or a spot of color, in just that patch.
Our brain then builds up complexity in layers. You have simple cells that spot the most basic stuff, like edges and lines. Then, complex cells take the outputs from those simple cells and combine them into more intricate patterns, say a corner or a texture. And finally, higher-level neurons put all those patterns together to recognize a whole object, like a face or a cat. This layered, hierarchical approach, that is the exact blueprint for a CNN.
Okay, let's move on to section 3 and open up the CNN toolkit. We're going to see exactly how this biological idea gets translated into a powerful piece of software. So, the absolute heart of a CNN is the convolutional layer. The best way to think about it is like having a whole set of tiny, digital magnifying glasses, which we call filters. Each filter is a specialist. It's trained to look for one very specific, tiny feature, like the curve of an ear, or a patch of fur, or a sharp angle. And this filter slides across the entire image, creating a new image, which we call a feature map, that basically lights up everywhere it found its specific pattern. Here's a perfect example to make that concrete. This little filter here is designed to do one thing and one thing only: find vertical edges. As it passes over a part of the image with a strong vertical line, boom, it outputs a high number. If there's nothing there, it outputs a low number. And here's the magic. The network learns which filters it needs all on its own. It might decide it needs hundreds or even thousands of these little feature detectors to do its job. Okay, so after creating all these detailed feature maps, we have an enormous amount of data. That's where the pooling layer steps in. Its whole job is to shrink things down, to downsample. It looks at a little neighborhood on the feature map and keeps only the most important piece of information. It's kind of like taking a whole paragraph of text and summarizing it down to one key sentence. And the effect of this is huge. I mean, look at this. A single common pooling operation can slash the amount of data by 75%. This not only makes the network way faster and more efficient, but it also helps it generalize by forcing it to focus on whether a feature is present, not exactly where it is. So finally, after many layers of convolution and pooling, the network has built up this rich collection of high-level features. It knows there are things that look like pointy ears and whiskers and fur present in the image.
The fully connected layer is the decision maker at the end of the line. It takes all of those identified features, weighs how important each one is, and then makes the final call, spitting out a probability. 98% chance it's a cat, 1% dog, 1% raccoon, and so on.
Okay, so we have the architecture down, but how do we actually make it smart? That brings us to Section 4, making the network smarter.
This is such a critical question. When you have a network with millions of knobs to tune, there's a huge danger it could just memorize every single cat picture you show it. But that's useless, right? We need it to recognize a new cat, one it's never seen before. This problem, memorizing the training data instead of learning the underlying patterns, is called overfitting, and it's one of the biggest challenges in all of deep learning.
Thankfully, we've got some really clever tricks up our sleeve. One is called dropout, where we randomly turn off some of the neurons during training. This forces the network to learn more robust features that don't depend on any single neuron. Another is data augmentation. We take our training images and create new versions. We flip them, rotate them, zoom in on them. It's like giving the network more life experience for free. And techniques like batch normalization help keep the whole training process stable and fast. All of these together force the network to generalize what a cat is, not just memorize pictures of them.
Now for the really exciting part, Section 5, CNNs in our world. Because this stuff isn't just a cool concept in a research lab anymore. It is all around us, and it is changing everything.
And one of its most profound impacts, happening right now, is in medicine.
CNNs are now being trained to read complex medical scans like MRIs and X-rays. And in many studies, they can spot the incredibly subtle early signs of diseases like cancer with an accuracy that can match and sometimes even beat expert human radiologists. This is a technology that is genuinely saving lives today. But the impact doesn't stop at the hospital doors. CNNs are also fundamentally changing how we get around, and even how we grow our food. The eyes of a self-driving car? Yep, that's a CNN, working in real time to identify pedestrians, read traffic signs, and keep track of other cars. In agriculture, CNNs analyze drone and satellite images to monitor crop health over massive farms. And in factories, they're on the assembly line, spotting tiny defects with a speed and reliability no human could ever match.
All right, to tie this all together, let's finish with Section 6, a simple analogy that will hopefully make this whole process really stick in your mind.
Just think of a CNN as a team of detectives solving a crime. The first few convolutional layers, they're like the forensics team on the ground. They're finding small individual clues, a footprint here, a fingerprint over there, a stray fiber on the carpet. Then, the middle layers are like the investigators back at the office, starting to connect those dots into meaningful patterns. And the final, fully connected layers? That's the lead detective, standing in front of the evidence board, looking at how all the patterns fit together, and finally solving the case. The object in this image is a cat.
So by mimicking the powerful, layered architecture of our own brains, CNNs have given machines a sense of sight that honestly used to be pure science fiction. They've moved from the lab into our hospitals, our cars, and our factories, solving real-world problems. And that leaves us with one final, very exciting thought. Now that computers can finally see, what on earth are we going to teach them to understand next?